Hello and welcome to the second part of the first lecture. In the first part, if you remember, we had discussed the approach to solve an algebraic equation iteratively. We are going to show now how one can apply perturbative approach in solving quantum mechanical problems. So for that, we discuss the perturbation approach for physical systems whose Hamiltonians are independent of time. So we will be discussing to start with only those type of Hamiltonians which are independent of time. That is why it is also known as stationary perturbation theory. So the name that we had given to our first chapter, that approximation methods for stationary states, is justified by this statement. Stationary perturbation theory. This method is applicable when the complete Hamiltonian is independent of time and can be written as a sum of two parts. So to start with, the Hamiltonian H for a quantum mechanical system, of course these are operators, can be thought of as two different summation of two different Hamiltonians. Let us write them as H0 and H1, where H0 is the Hamiltonian which we can actually able to diagonalize. So this is a diagonalizable Hamiltonian. That means you can exactly find out the eigenvalues of this Hamiltonian. We can determine the eigenstates of this Hamiltonian H0 also. And this Hamiltonian you will find in many books as to be determined or defined as unperturbed Hamiltonian. Unperturbed Hamiltonian, or free Hamiltonian, or solvable Hamiltonian. So we have a Hamiltonian. Let us recall what we do in quantum mechanics. We first try to figure out what system we are dealing with, then we generally try to find out what is the Hamiltonian. For example, in case of harmonic oscillator, you had p square by 2m as the kinetic energy term, and then half m omega square x square as the potential energy term, and you write down the total Hamiltonian of the system, and then you try to solve for the energy eigenvalues and energy eigenstates for those Hamiltonian. So those particular problems for which you exactly are able to solve the Hamiltonian will construct this H naught. Then you will ask, what is my H1? This H1 should therefore be nothing but the perturbing Hamiltonian. This is the perturbation or perturbing Hamiltonian. Or also sometimes called correction to H0. So our Hamiltonian has two parts. The first part known as the solvable Hamiltonian or unperturbed Hamiltonian or H0. The second part is a small correction to it. Now when I say correction, what do we really mean by the word correction? Classically, if I write down the correction as H1, and then we could say whether this correction is numerically always small compared to this H naught or not. Generally, H1 is always small compared to H0, and to keep track of how big this correction is, we generally introduce a parameter which is very small. So let me explain it once again. So we have this Hamiltonian which has been divided into H0 and H1. Now, if the perturbing Hamiltonian is small, then these eigenstates and eigenvalues would be very close to the unperturbed Hamiltonian eigenstates or eigenvalues. Thus, one can expand these quantities in powers of the effect of the perturbing Hamiltonian. What do I mean by that? So, let us write a little bit more explicitly. So, suppose, as I said, this is a diagonalizable Hamiltonian or unperturbed Hamiltonian. That means we know exactly what are the solutions. That means we know exactly the energy eigenvalues for H0, and we also know the eigenstates. That means I know H0 acting on N0 is equal to En0 N0, where N0 denotes the eigenstates of H0. Let me write everything clearly. So these are the eigenstates of H0, and the En zeros are the eigenvalues of H0. This 0 implies there is in everywhere in superscript or subscript we have written 0. This 0 implies that this corresponds to unperturbed Hamiltonian. It does not mean anything else. Now we also have said that we are discussing the non-degenerate perturbation. That means corresponding to each state N or N0, we have a single value of the energy. There are no two states with the same value of the energy. So the degenerate case has to be discussed separately, but for the time being we assume that all states are discrete and non-degenerate. So from now on the assumption is all states are discrete and all states are non-degenerate. That means none of the two states or more states, none of the two or more states have the same energy eigenvalues. Because of the perturbing Hamiltonian H1, the total Hamiltonian H should now have a new set of eigenstates, because this is my total Hamiltonian. This capital H is my total Hamiltonian for the system. We only know H0, which is the unperturbed Hamiltonian, its corresponding eigenvalues and eigenvectors, but we really do not know at the moment what are the eigenvalues and eigenvectors corresponding to H1. Now, because of the perturbing Hamiltonian H1 is there, the total Hamiltonian H should now be having a new set of eigenstates N. So H should have a new set of eigenstates which let us denote by N, ket N, and they should also have a new set of eigenvalues which we denote by En. Now if the perturbing Hamiltonian is small, if the perturbing Hamiltonian is small, then these eigenstates and eigenvalues would be very close to the unperturbed state and eigenvalues. Right? Think about the example that we had given. So let us just recall the example of the discussed in the previous class. Although it was an example corresponding to solving an algebraic equation, but still it is good. So this is of course not a part of this main discussion. I just want to remind you. So we had xs cube minus 4.001 x plus 0.002 is equal to 0. This was the algebraic equation. There we had introduced a parameter which is very small and we called that epsilon, and we choose the value of epsilon to be 0.001. Then this whole equation was written as x cube minus 4 plus epsilon x plus 2 epsilon equal to 0. And then we said, since this epsilon is very small, it's almost very nearly equal to 0. So we can think of this term to be 0, and we can, to the epsilon to the power 0th order, we can simply look at the equation x cube minus 4x equal to 0. And we saw that the root of that equation was 0 and plus minus 2. Then we said, since this is not exactly equation which is x cube minus 4x equal to 0, rather it has something else which is 4 plus epsilon, where epsilon is small, and then there is an extra term plus 2 epsilon with epsilon being small. So the root should be very close to 0 and plus minus 2, but it is not exactly 0 and plus minus 2. And then we had figured out perturbatively, or we had figured out iteratively what the root should be. And if you remember, we had figured this out in the previous class. And one of the roots came out to be minus 2.0005. It's extremely small. Still, it is not the same root as you have obtained if your epsilon was 0. Exactly same procedure, exactly same method you can apply here. If the perturbing Hamiltonian is small, then these eigenstates and eigenvalues would be very close to the unperturbed values corresponding to this H0 Hamiltonian. But it will not be same as the eigenvalues and eigenvectors corresponding to H0. That is clear. Thus we can expand these quantities in powers of the effect of the perturbing Hamiltonian. However, since the Hamiltonian is an operator, we cannot use it as an expansion parameter. Here comes the difference. Classically, you can always choose, or you can always say if your Hamiltonian is small or large compared to some other Hamiltonian. Generally, this Hamiltonian H1, which is the perturbing Hamiltonian, is always small compared to H0. And to keep track of how big this correction is, you introduce a parameter lambda. So first let me write, then I will again explain. You write the thing as h equal to H0 plus lambda H1, where this lambda is a very small parameter. And it is sufficiently small such that lambda H1 serves as a correction to H0. So it is sufficiently small such that this lambda H1 together serves as a correction to H0. So it's very small. But as I said already, since H0 and H1 are operators, So what do we mean by small may not be very clear immediately, because these are just operators. How can we compare between two operators? If you want to think of them, you can think of them as infinite dimensional matrices. So how can you say what is small and what is large? So we can think of it in two ways. Either we say lambda is a parameter, say some real number, which is very close to 0, and h0 and h1 are comparable to each other. That is one way of saying it. Or we can simply set lambda to be equal to 1, and h1 is such that all its matrix elements are small compared to the matrix elements of h0 in some given basis. So these are the two ways of looking into this equation. Either, let me tell you again, either we say lambda is a parameter, maybe some real number which is very close to 0, and h0 and h1 are comparable to each other. Or the second way is to think of lambda to be equal to 1, and h1 is such that all the matrix elements of h1 are small compared to matrix elements of h0 in a particular given basis. Then only it is meaningful to say h0 or h1 is small compared to h0. Now once we have written this like this, h as h0 plus lambda h1, we would like to keep lambda as a smaller parameter, because we would like to keep track of orders and they would refer to powers of lambda. So this is very important. Remember, again, go back to the discussion that we had earlier in the discussion of the solution of the algebraic equation in the first part of this class. There, what we did in order to find out the solution, we actually wrote down the solution as a series solution, and we had written there as x equal to sum over n equal to 0 to infinity epsilon to the power n xn. And then we actually wrote this as epsilon to the power 0 x0 plus epsilon to the power 1 x1 plus epsilon to the power 2 x2, like this. And at each order we just simply put this series to the original expression of the equation and tried to figure out what are the roots at each and every order. Exactly same process you should apply here. We would like to keep therefore this parameter lambda as a small parameter, because we would like to keep track of orders in the perturbation theory, and they would refer to as powers of lambda. Now we have to keep one thing in mind. We always work with Hermitian operators in quantum mechanics. Here also h0 and h1 both are Hermitian, and lambda is a real number, such that the eigenvalues of h remains Hermitian. That is another important aspect of this thing that you should always remember. Because we need real eigenvalues, we need to work with Hermitian Hamiltonians. Therefore, h0 and h1 both should be real and both should be Hermitian, and lambda should be real. Now, we can expand various quantities in powers of lambda, but I would actually, before going into the discussion, I would again very briefly like to discuss something else. Given the eigenvalues and eigenfunctions of h0, can we find out the eigenvalues and eigenfunctions of h? That is the question that we should first ask ourselves. Remember, the eigenvalues and eigenfunctions of the correction or perturbation is not known, as I have told. This is trivial if h0 and h1 commutes, because we can simultaneously diagonalize two commuting observables and find out a common set of eigenvectors. Do you remember that? If not, again, please go back to the previous year's quantum or previous semester's quantum mechanics course. It was a very, very standard theorem which states that if two operators commutes, then we should have a simultaneously diagonalizable this we can simultaneously diagonalize these two commuting observables and find out a common set of eigenvectors. Therefore, this part is not interesting if H0 and H1 they commute. Let me again explain. If these two operators, if they commute, then the problem is trivial. Why? This is because if two observables represented by two operators, if they two commute, then we can simultaneously diagonalize the two commuting observables, because we can simultaneously diagonalize two Hermitian observables represented by two Hermitian operators and find out a set of common eigenvectors. This was a theorem that you have already seen in your previous course. Therefore, if this and this H0 and H1 commutes, then the problem is completely trivial, because I have already told that H0 and its spectrum is known to you. So if H0 and H1 commutes, by knowing H0 spectrum you can immediately figure out what should be H1 spectrum because of this theorem. So in order to complicate your life, you can actually work with, or you can actually think of solving problems where this H0 and H1 do not commute. So just to set the stage of our broader discussion, let us start with a very simple example. All of you, I suppose, have heard the name two-state system. If not, again, I refer to go back to the previous semester's discussion. I remember, and I was told by Charu sir that he has discussed this two-state system in depth. So let us start with a two-state system where this H0 is represented by a 2 cross 2 diagonalized or diagonal metric, where U1 and E2 are two distinct energy eigenvalues, and it is already diagonalized and it is written in its eigenbases. They have, this H0 has two eigenvalues, U1 and E2, and as I already said that when I give you H0, that means the eigenvalues and eigenvectors are known to start with. Then if H1 is not diagonal and does not commute with H0, then we have some calculation to do. So suppose I give you a perturbing Hamiltonian which is not diagonal and which does not commute with H0. So H, which is H0 plus lambda H1, is nothing but U1. If I multiply, then this term will be simply lambda, this will be lambda, and this will be E2. So this will be my total Hamiltonian of the system, where this is known, this is the unperturbed Hamiltonian. We need to find out the spectrum. That means we need to find out what should be the new eigenvalues. Now the eigenvalues for the total Hamiltonian capital H can be determined in the usual way. It's very easy. First note that due to addition of perturbation H1, the eigenvalues of H will no longer remain U1 and E2. It should be different. They will be certain function of lambda, just like when we wrote down this equation, the solutions were functions of epsilon. Here also the eigenvalues will be functions of this small parameter lambda. And in addition, we know how to find out the eigenvalues of the matrix. So how to find that? You write down this, that u1, suppose this eigenvalue is delta, so you write it like e1 minus delta and lambda e2 minus delta. You know how to figure out the eigen values of a matrix, that too a 2 cross 2 matrix. It's very easy. So let us calculate this thing. This is e1 minus delta into e2 minus delta minus lambda square equal to 0. So this is going to give us e1 e2 minus delta into e1, there will be one term, and then delta into e2, so delta e1 plus e2 will be the term, and then there will be plus delta square minus lambda square. Okay, and remember we are solving for delta. So delta, it's a quadratic equation in delta. e1 e2 are known, lambda is a small parameter, so everything will come out in terms of lambda and e1 and e2, and there will be two roots because it is a it is a quadratic equation. So we write the roots as delta 1 and delta 2. So this is going to give us minus b, so this is e1 plus e2 plus minus root over b square minus 4ac. So this is e1 plus e2 whole square minus 4 e1 e2 minus lambda square divided by 2a. So divided by 2. A is 1. So this is what we are getting. So now if we simply calculate this, this is going to give us e1 plus e2 plus minus square root e1 square plus e2 squared plus 2 e1 e2. Okay, this is okay. I should not have written all these steps. This is very easy. I did not notice it. So this is divided by 2. This is nothing but e1 minus e2 whole square. So this is, sorry, let me go to a new page. So delta 1 comma 2, it should be e1 plus e2 plus minus square root e1 minus e2 whole square plus 4 times lambda squared divided by 2. Now suppose your e1 is greater than e2. Then what happens? Delta 1 comma 2, it will simply be half e1 plus e2 plus or minus e1 minus e2. I will expand this thing, 1 plus 4 lambda squared by e1 minus e2 whole square to the power half. I mean, we can actually write this if lambda is less than e1 minus e2. Then this is going to give us delta 1, let us write just the plus sign root. This is going to give us e1 plus e2 plus e1 minus e2, and then there will be something like 1 plus half into 4 lambda squared e1 minus e2 whole square term, and then there will be lambda to the power 4th order terms. There will be all these things. So what I did here is very easy to understand. I simply took this e1 minus e2 whole square as common outside the square root. Therefore we have here 1 plus 4 lambda square by e1 minus e2 whole square to the power half. Then I assumed that this lambda is even smaller than the difference between the two eigenvalues e1 minus e2, and then I expand this binomially. So I will get, so this e2 gets cancelled, and we will get this one correction to energy as e1 plus lambda square divided by e1 minus e2 plus correction terms of the order of lambda to the power 4, then there will be terms like lambda to the power 6 and going like that. So the important point to note in this particular example is, even though the small parameter lambda was linear in the Hamiltonian H, remember H had simply e1, lambda, lambda, e2. These were the entries of the Hamiltonian matrix. Even though the small parameter lambda was linear in the Hamiltonian, if we compute the eigenvalues, we have all powers of lambda. That is the one thing that you need to figure it out, not figure it out. I mean, that is one thing which you need to understand very clearly. So this, let me put a box. Now, similarly, if you calculate delta 2, this will come out to be e2 minus lambda square by e1 minus e2. Okay. Yes. Okay. Yeah. Actually, I did a wrong thing. I should not be, I am not allowed to, I didn't notice that this is a product. This should be e1 minus e2 plus e1 minus e2. What will happen here is that this e1 minus e2 will get multiplied with this 1, and then e1 minus e2 whole square term will get cancelled. 1 e1 minus e2 will remain in the denominator, and then we will have terms like e1 minus e2 plus e1 minus e2, and there this 1 e2 will get cancelled. I should not have cancelled it before multiplying. That was wrong, but the answer is this. So if you choose this negative sign, that is the second root, this will again be like this with a minus sign here. So even if the Hamiltonian is linear in lambda, the eigenvalues in general, we expect an infinite series in lambda. The corrections to eigenvalues of order lambda, lambda square, lambda cube, lambda 4, in this way it will remain. But for example, in this particular example, you can see that once you have this lambda to the power 0 term, lambda to the power 0 term always comes with the unperturbed energy, and then there is no lambda order term. Sorry, what did I do? There is no order lambda to the power 1 term. The next term that comes is lambda square. Then there is no lambda cube order terms. So the correction to the lambda cube order is 0. Correction to lambda order term is 0. But there is a second order correction to energy, which is lambda square. Then there will be a term which is lambda to the power 4 correction, and so on and so forth. In this particular problem, therefore, the odd powers of lambda vanishes. So this example in particular actually helps to understand a few things. So when H1 can be said to be small compared to H0, what did we understand from this problem? Can we understand anything from this problem? Can we now understand something just by looking at this particular example? It's not sufficient to say that the off diagonal element lambda is small compared to E1 and E2. There is a tendency that just when we write down the solution in this problem, we can simply say, oh, there was this lambda term there in the off diagonal element. Here there is this lambda, and lambda was small, or here is this lambda was small, so lambda should be small compared to E1 and E2. Just by looking at the total Hamiltonian matrix, that is matrix for H, you might be tempted to say that we can make a perturbative expansion as long as the off diagonal elements are small compared to the diagonal components or diagonal elements. But you are absolutely wrong there. Actually, lambda has to be less than, much less than E1 minus E2. That's what we have just found out. We have just found out that if lambda is small compared to E1 minus E2, then only we are allowed to do this expansion. Therefore, lambda must be small compared to the differences in the energy eigenvalues. That is the first thing that you should note. So, looking at the problem, you might be tempted to say lambda is much small compared to E1, lambda is much small compared to E2, but that should be, or that will be wrong. The correct thing is that lambda is much small compared to the difference between E1 and E2. Now, secondly, this method is not true if this method will not work if E1 equal to E2. That means that for the degenerate case, we need a totally separate method for that, and we need something called degenerate perturbation theory. But let us see why this will not work. What happens if E is equal to E1 equal to E2 in H0? Then what happens is this. Then your total Hamiltonian H is nothing but H0 plus lambda H1, which is nothing but E lambda E. In order to find the eigenvalues, what should you do? You simply write down this characteristic equation, E minus delta lambda E minus delta, and then this is equal to 0. You try to solve this. What you get is E minus delta whole square equal to lambda square. What is the problem if we have E minus delta square equal to lambda square? Because you can simply write down, because you are looking for the eigenvalue delta, no? So you can simply write down, okay, my solution is E plus minus lambda. Firstly, the character of the eigenvalue changes completely. It is correct to all orders in lambda, and that is an exact result. So the infinite series has collapsed so that you only have E plus lambda and E minus lambda as the eigenvalues. This again illustrates a general principle. If we have a degenerate energy level, and then if we switch on a perturbation denoted by the off diagonal terms of the Hamiltonian, then the eigenvalues are split into two, E plus lambda and E minus lambda. This is a general feature of perturbations in case of degeneracy. In general, we need to handle more complicated system. This was just an example with a toy model. We will come back to the degenerate case in a little bit more discussion, or we have a completely separate discussion. But as I already said, that if you have a degenerate energy level, what happens is that you just switch on the perturbation, then your energy level just splits into two exact E minus lambda and E plus lambda, and this was the original eigenvalue of the Hamiltonian H0, which was degenerate. This is where you are turning on a perturbation by switching on some off diagonal elements, and immediately what you see is that the degeneracy got lifted. Now you have two separate energy levels corresponding to E plus lambda and E minus lambda after we have switched on the perturbation. This case therefore requires a completely different approach, and that we will come a little bit later, maybe after 4 or 5 classes. And also, as I said, in general we need to handle more complicated systems, so we need to have a clear prescription to follow in the most general way possible, that we will come to in the next class. For that we will actually do from the very beginning the calculations required to find out what should be the corrected energy levels and what should be the corrected eigenvalues, eigenfunctions of a particular perturbing Hamiltonian. That is coming next.